Alkanes, alkenes, and alkynes. Now, alkanes were the ones with the single carbon-carbon bonds. Alkenes were the ones that had a double bond. And now alkynes are the ones with triple bonds in the carbon-carbon chain. Now, just like with alkenes, alkynes are also referred to as unsaturated hydrocarbons, because as soon as you add in a triple bond, you have to lose hydrogens in order to maintain that 4-bond maximum that carbon has. Among the three, alkanes, alkenes, alkynes, we say that alkynes has the highest degree of unsaturation because in order to have a triple bond, you have to lose 4 hydrogens in an alkyne. So let's draw a simple structure. Here is a carbon backbone. I'm going to put in a triple bond here. Now let's put in the number of hydrogens. As usual, every carbon can only handle a maximum 4 bonds. So you see how we have this empty space in these regions. So adding a triple bond makes you lose 4 H's in total. So here is the full structural diagram of an example of an alkyne. Okay. For alkynes, if we were to do this in a condensed structure, it would be CH3, so that's the first grouping there, CH3, followed by a CH2, that'll be this group here, followed by a C, and then a CH3. So you can identify a triple bond within a condensed structure if you just see 2 carbons next to each other side by side. That would be indicative of a triple bond. You may also see alkynes exemplified with a slightly expanded condensed structure where you add in some bonds and it would look like this. Now the line diagram for triple bonded carbon-carbon backbones is a little bit unique. When we look at an alkane, the carbon backbone takes on a natural zigzag shape, and this is due to the Vesper arrangement of that carbon atom that has 4 attachments around it. So in a line diagram, we draw the backbone of the carbons only, and so we get a zigzag shape. Here we have an alkene where one of the single bonds has been replaced with a double. We can see that the structure retains its zigzag shape. Over here on these 2 carbons, if you remember back to Vesper, when a central atom has 3 attachments around it, the structure takes on a trigonal planar structure. Trigonal planar, as a reminder, is like a triangle with each of these angles at 120 degrees. We have 2 of them, 2 trigonal planars side by side, and so these help in maintaining that zigzag shape of the molecule, and the line diagram will still look like a zigzag. Now let's look at an alkyne. Now when we add in that 3rd bond and make a triple bond, we notice that our zigzag shape disappears. And what happens is we get this nice stretch of a linear structure happening in this molecule. Now remember back to Vesper that when a central atom has 2 parts connected to it, the structure takes on a linear shape. And this is actually what's happening in the middle here. Both of these carbons have 2 things attached to it. So there's the center, and there's 2 attachments. So is this one. If that's the center, then there's 2 attachments. And so altogether, when you have a triple bond, a structure loses that zigzag kink and straightens out into a linear section. So how do we draw the line diagram for an alkyne? Well, we look at this structure here. This is a 5-carbon chain with a linear section following in this region here. So we have our 2 carbon first, so that's our line for 2 carbons, and then we draw the linear section. If we were to follow the carbons, you have carbon 1, that's right there, carbon 2, that's right there, 3 and 4 are going to be the triple, and 5 is going to be our end carbon. So where is that triple? Well, it's going to be right in the middle. It looks funky, but there's 3 and there's 4. You don't have to worry about isomers in alkynes. There's only one way it can look like. which is the linear structure there. And this is because triple bonds are extremely stiff because there's so much attraction going on there. It's a sharing of 6 electrons, and as such, these triple bonds are highly rigid and they cannot rotate. So the structure is locked in to look linear, like so. Let's talk about naming rules. Now the naming for alkynes is actually rather simple and straightforward. It's very similar to the alkenes, except it doesn't have any of that silly cis and trans business. Okay? So here we go. Here is a alkyne. The triple bond takes priority, just like the double bond takes priority in an alkene. We try to keep the number as low as possible for that triple bond. So we see that numbering it from the right results in the carbon receiving a 2, where that the triple bond first occurs. So this is going to be 2 dash, and this is a pentane, but instead of a pentane, we say 2-pentyne. Perfect logical sense. Let's do another example. CH3, C, C, CH2, C, C, and H. Here we have an alkyne with 2 triple bonds, and much like the alkene system where we had a diene, we can have a diene. Number 1 rule, we keep the numbers as low as possible. So the best way to do that would be to start from the right, and you get carbon 1 there, 2, 3, 4, 5, and 6. And that results in our structure having the triples at position 1 and position 4. This is much smaller than if you were to number the chain from the left, and which would have resulted in a numbering system of number 2 and 5. So 1 and 4 clearly is the better option. So this structure is going to be called 1, 4 hexadiene. And again, the di means 2, and that prefix is occurring right before the thing that it's doubled, which is the Y and E part, standing for triple bond. 1,4-hexadiene. Let's go ahead now and take a look at some line diagrams. Okay. Well, number 1, the triple bond takes priority, which makes numbering way easier than numbering alkanes. We have to worry about the pathway and what gets the lowest number set. When we have an alkyne, straight up, you number the chain with the lowest number at the carbon with the triple bond first occurs. So that pretty much takes care of it. We're going to go from the right. Okay. And so we name our branches, just like in alkenes, branches first. This is going to be 4-ethyl. Then we put our numbers down for where the triple bond is happening. This is going to be 2. This is a 7-carbon chain, so it's heptyne. Now let's look at some exciting structures. Let's do a fun one. Let's do a fun one. I call this Phoenix Rising through the fire. Anyways, let's number the chain here. Either direction you go, it's going to be 1 and 4. Even if you went from the left, it still would be 1 and 4. You can count that to prove it to yourself. Let's number and label the branches. We have 2 branches at position 3. We have an ethyl and a propyl. By the rules of the alphabet, we're going to number and label the ethyl first because E before P. So this is 3-ethyl, 3-propyl, followed by our numbers of our triple bond. This is going to be 1, 4. This is a 5-carbon chain, so penta. There's 2 triples, diene. 3-ethyl, 3-propyl, 1,4-pentadiene. Certainly is a mouthful. Let's do one more example. Oh my god, a circle! Just like with alkenes, we are going to number this starting with 1 at our triple bond. Now remember that we need to number carbons across the triple bond and not skip it. So our choices are, if we want to go clockwise, 1, 2, 3, 4, 5, and 6. If you want to go counterclockwise, this will be 1. Going across the bond, this will be 2, 3, 4, 5, and 6. Which one are we going to choose? We are going to choose the clockwise one because we see that if we choose these numbers here, our methyl branch gets 4 instead of 5, which is a lower number set. Alright, branch first. This is going to be 4 methyl. 4 methyl. Now, we could write 1 followed by cyclohexyne, but since there's only one triple, and that triple is automatically going to be numbered 1, it would be redundant to write number 1 for what that triple bond is. So we simply write 4-methyl cyclohexyne. No 1 necessary. So there you have it. Alkanes, alkenes, and alkynes. Boy, we're having all kinds of fun today. Boo out.